Good evening, everyone. Thank you so much for joining in today. We will begin in a couple of minutes. Thank you. All right, I think we can get started. Good evening, everyone. I welcome you to the webinar on cost estimation and affordability for your building. I am Yashima Jain, and I'll be moderating today's session. Before we begin, I would like to acknowledge the support of Department of Science and Technology, Design Builder, and MacArthur Foundation. I would also like to acknowledge our affiliates and CSR support. For today's session, we have two experts joining us. First, we have Mansi Parikh, who will talk to you about how you can use your energy model to estimate the cost for your project. Mansi is a senior sustainability consultant working in the field of sustainable design. She has key qualifications in the field of passive design, low energy cooling, and HVAC systems. She has worked on various projects with goals leading to net zero energy, water, and waste. For our second session today, we have Jagdish Talluri with us. He will talk about how to assess the cost for your building, calculate the return on investment, and help you make it more affordable. Jagdish is the CEO and founder of 1EQ EduTech Private Limited. He is an architect and an IIM Calcutta alumnus and has over 19 years of professional experience in the design and development of large-scale corporate and institutional projects. He has spearheaded notable projects such as the National Secretariat Complex for the Royal Government of Bhutan and Suzlon One Earth campus in Pune. He was trained in advanced energy simulations and low energy HVAC design by various international experts and US national labs. We welcome you today, Mansi and Jagdish. And for our participants, as always, you are free to send in your questions at any time during the session. We will take as many questions as time allows us at the end of the session. And with that, we can get started. Mansi, you can now share your screen. You're on mute, Mansi.
Okay. Sorry. Yeah. Is my screen visible? I would believe.
Yes.
All right. So, hello everyone. Energy simulation has been plays a major role when we are calculating for the costs and for energy savings, calculating for energy savings as well. So, so as you can see that from from any particular model, we can get various sort of information like calculating. Sorry, in this particular session, we'll be discussing about what we can get, what sort of information which we can get from energy simulation model, calculating first cost savings for energy for a particular ECM, cost savings due to system sizing, and again, a fundamental or on details of net incremental cost. So, this is energy split for a typical office building. This building is located in Vishakhapatnam for total around 8-hour operation. And these is the kind of data which we get from a simulation model, like what would be the total electricity consumed in kWh. Here you can see in black is 8 lakh kWh total. And based on that, what we can do is calculate the total energy cost. So here in this particular city, the energy cost unit per unit was approx 10 rupees. So the total energy consumed, which was calculated, was around 83 lakh rupees per annum. Again, from the model, we can get these splits. So say this is an office building. So more or less, typically the 50% or more of the energy is consumed here in cooling, as you can see, and further it is divided between equipment and lighting. We can also get the peak electricity which can be used, or what would be the amount of cooling capacity required. So here around, so 200 ton of refrigeration was required for this particular building. And after even providing, cooling system, if there are any sort of there would be hours where person might feel uncomfortable beyond 26 unmet hours. All of this data which we can get from energy simulation model. So once we start talking about energy conservation measures, a typical question, or the first question which we get from developers, would be what would be the first cost, or what would be the energy savings which I get. So say if I'm putting insulation on the roof, then what would be the energy savings which I would get annually? So here in this particular chart, what you can see on the x-axis is the roof insulation. So there are 3 cases. The case 1 has no insulation. Case 2 has insulation on roof of 0.9 mm. 0.9 watt per square meter per Kelvin, and the case 3 has U value of 0.4, which would require around 25 to 30 mm of insulation on the roof. On the x-axis and on the y-axis is the annual electricity cost in rupees. So here in this, we can see that by providing insulation of around 15 mm, which would give you U value of 0.9, we can save annually of 1.3 lakh. In annual electricity bill, that would roughly around 1.6%. And even if we provide 25 mm of insulation, we can, get the cost savings annually of 1.8 lakh here. So these are the kind of numbers which we can get from our energy simulation model, which would help us in convincing our clients and to choose the correct energy conservation measure. So apart from this, what I did was, check, this was only roof measure. There are other sort of energy conservation measures which can be incorporated for roof, wall, energy efficient glazing, reflective coating on the roof with high SRI paints, or providing shading for the windows. So these were a couple of other parameters which I studied for this particular building. You can here see I checked for various U values for walls, roofs, shading devices, say 0.3 meter to 1 meter width. These were all the envelope measures. Now, what I also studied for this particular project was, what could be the various COPs for different kind of HVAC systems, like VRF system, split air conditioning unit with various star rating which are available in market from 3 to 5. Checked for lighting measures with various kind of lighting power densities, reducing that to ECBC super level, providing various kind of controls, occupancy, programmable timing controls, all of that. These were also studied. The similar studies can be done for these sort of measures to, arrive at the energy savings. So so after this, what I did was, to understand which energy efficient measure to choose. So here on for this particular graph, on the x-axis, you will see various, say, U values. These are all roof U values from zero point 0.9 to zero point 0.2 watt per square meter. On the y-axis is annual electricity bill. Here you can see what are the kind of savings which we can get by incorporating these U values in the roof. So here for 0.9 U, one would require, say for 200 mm slab, one would require almost around 15 to 20 mm of insulation. To same here, when we are trying to achieve the U value of 0.2, where we are getting a higher amount of energy saving of 1.8 lakh rupees, the amount of insulation required in this case would go around 100 to 125 mm. That depends on the kind of insulation again. There has been always a cost. So there would be, so here is in this graph, you can see that for each of the energy conservation measure, there has been energy savings, but however, there is a cost attached to the same. So there is a term called net incremental cost. So that is nothing but incremental cost. That would be cost of labor and material to incorporate a particular ECM minus the cost of reduction in system sizing. So say how we calculate incremental cost. So for this particular ECM, for say roof, what I did was, for a particular building, what I did was calculate the roof area which would be required, and based on that, calculated what would be the insulation thickness. Based on the insulation thickness, came with the cost attached for 0.9, 0.4, 0.3, 0.2 zero point 0.2 U value meeting insulation. And then and again, did a little bit of market survey to understand what would be the cost implication for the applying of that insulation. So that would also, so the incremental cost would also include the labor cost. The other part is cost reduction in system sizing. So, for a typical room, if you say it's on, say, last floor of the building or end floor, I would say, but if there is, say, 2 tons, so if it's 200 square feet of a room, the tonnage of refrigeration required would be around 2 tons. If we provide insulation on the roof, there would be reduction in the percentage or the reduction in the tonnage of refrigeration required. So say that would be X. So previously, the tonnage of refrigeration required or the split AC tonnage required was 2 tons. Now, after providing insulation, the tonnage of refrigeration required would be 2 minus X. So say that X would also have a cost implication. So say now we require 1.5 ton instead of 2 ton. So say the 2 ton of split AC would cost you around 65,000 when you go to a market. And when you go to buy 1.5 ton of refrigeration, that is going to cost you around roughly 40,000 rupees. So there has been a difference in this cost. So that is nothing but the cost in reduction of cost in system sizing. So again, here this explains the similar thing, this graph. So on the x-axis here is the tonnage of refrigeration for this particular office building, and on the y-axis is here you can see there are multiple cases with no insulation, with 15 mm of insulation reaching U value of 0.9, further reducing to the U value of 0.2. And these are the reduction in system sizing required. So here with no insulation, we required almost 200 or 180 tons of refrigeration. When we provide insulation of say 15 mm, we reach the U value of 0.9, we get the reduction in system sizing is almost 8 TR. So that would have reduction in the cost sizing. So that is nothing but the cost reduction in the system sizing in the formula. So in this particular chart, there are the bars in green is the cost reduction in system sizing, and the bars in blue is the incremental cost. On the left here, you can see the various roof insulation U values from 0.9 to 0.2, and these are the cost. So here, what you can see is that, for reaching U value of 0.9, the cooling capacity savings is 4 lakh rupees. And similarly, the cost of insulating this is around 3 lakh rupees. Similarly, for 0 0.5 to achieve U value of 0 0.5 watt per square meter Kelvin, the cost, incremental cost is 5.7 lakh. However, the cooling capacity savings it is providing during the selection of the equipment, it is 5 lakh rupees. So your net incremental cost is the difference between both of these. So in this particular case, say for 0 0.5 watt per square meter U value, your net incremental cost is 5.7 lakh minus 5.19. That would be around 50,000 rupees. So that is going to be your net incremental cost. So again, say for this particular case, however, that this cost, net incremental cost is negative, because your cooling capacity saving is almost 1 lakh higher as compared to what you are spending on incorporating the roof insulation. So definitely this measure is going to, this is going to be cost free, as a net incremental cost is in negative. So this is going to be very beneficial. So definitely roof. So in this particular case, it is very much advisable to go for the roof insulation. So to derive at these kind of costs, a market survey was done. So what we did was here, at this particular point, we calculated what would be the roof area which would be required, and based on that, what I did was market survey to understand what are the kind of insulation which are available in market. Rock, wool, XPS. We contacted various companies like General Petrochemicals, Dow, Owens and Cornings to arrive at the cost of these all insulation. And based on that, the square cost was calculated for each of the case. And this talks, after this, there are other information which one can get from an energy simulation model, like when I do any sort of cost calculation, or when I do sort of area calculation, I do never go to the plans. I directly get these numbers from the energy model, like the area of room, total area, to do daylighting calculations, or cooling capacity saving, system sizing. All of that can be directly, we can get from the energy model. Again, say if you are doing water calculation, so water consumption for cooling towers or evaporative coolers can be again derived from an energy model. So one interesting, however, we are building towards resiliency. So say if we want battery capacity for a resiliency, using energy, if you want to see what would be the battery capacity for a daily use, we can get it from the energy model. So this is a typical example where, for a school, for a school building, what happens is, during the daytime, the major energy guzzlers would be lighting and electricity. If it's going to be mixed mode operation, then we can only limit the battery to the electric equipment and lighting. Cooling can be incorporated if it's going to be mixed mode application here. So this is it from my side, Yashima.
Yeah, thanks,
and we are
Mansi.
open for questions.
Yes, thank you so much, Mansi. That was a very interesting session. There are no questions here so far, so I'll pass it on to Jagdish for now, and then we can take all questions towards the end of the session.
Oh.
Yeah, thanks. Jagdish, you can share your screen.
Yeah, just 1 minute.
While you share your screen, we have a hand raised, and I would allow our participant to ask their question. So, Varad Mandhani, you can unmute yourself and ask a question, if that's what you raised your hand for. All right. I think that's by mistake. We'll proceed. Jagdish, you can share your screen and we can begin. Thank you. Yeah, your screen is visible. Yeah.
You can see my screen?
Yes.
Okay. Perfect. So just a minute. Yeah, so welcome everybody for the expert lecture on affordability. Something. Yep. Yeah, in this webinar, we will not be covering the topics that you have already learned in the self-learning module. I am assuming that all of you have gone through the self-learning module to understand the difference between project budget and project cost. What is a hard cost? What is a soft cost? And what kind of cost estimations are there? How you can do and what kind of things are to be done in that? And how you can do rate analysis, quantity takeoffs, what kind of categories and classifications of project estimates are there. I'll not be getting into these aspects. In this webinar, I'll be taking you through some examples and case studies on my take on affordability, how you can, creatively work on these things. Before we go further, first of all, we have to understand what is affordability. Affordability doesn't mean you must be hearing affordable housing. It's not like low cost. Affordability doesn't mean low cost. Affordability is like almost like value for money, like state of being cheap enough for people to be able to buy. And in this webinar, that we'll understand how you can make your net zero energy buildings affordable, how you can convince project partner, how the mindset of project partner works, what kind of issues they deal with and all. So the project partner expectations are usually quite simple and straightforward. Everybody is going to see like what they're going to receive for what money they are spending. What is my return? And is it worth the money that I'm spending? And do the returns justify the cost that I'm incurring right now? Because everybody is worried about the capital cost that you are spending today more than the operational cost that they'll keep incurring year on year later. So these are the 4 fundamental questions. In one way or the other, your project partners may be asking, or in return, in future also, your jury also will be looking into the similar kind of things. And now, when it comes to the contest, how are you going to be judged in the affordability contest? What are the requirements? So the jury is essentially going to look at how you are optimizing the construction cost, what kind of strategies you are using, and how you're going to optimize financing costs or soft costs, and are you relying on any life cycle cost analysis to prove your point. But if you see from the project partner perspective, so there, like in this table, I have shown like 3 sort of purposes like these people may be having. One is like people are building so that they can sell it off. Like, for example, you can say single family housing, multi-family housing will fall in that kind of category. And the project partners' expectations will be, they want to sell it for the maximum amount of money that they can get. And they want to incur as less capital cost as possible. And other purpose will be build, own, operate, or lease. So these are typically office buildings, or you can say construction worker house. So these people, they'll build, they'll own the asset, they'll also operate or lease it. Like, for example, DLF has a lot of office buildings. They don't use the office buildings for their own purpose. They're building, they're owning, and they're operating, and they're either leasing it to somebody or they're using it by themselves. So in this case, the people who are into operation or lease, they are basically interested in the rental income. How am I going to, increase the user experience so that I'll get better rental than the next guy? And how much less I will spend for the maintenance. So this will be the kind of expectation that the project partners with this building typology will have. And the most common project partner type that you may be having is this. They'll build, they'll own, they'll either live or they'll use it. So for example, single family housing, multi-family housing also may fall in this category, because if it's a cooperative housing, if you're if your project partner happens to be a cooperative housing group, so they may be owning and building for themselves. So it's not only developers. And office buildings also, like in case of people like Infosys or Wipro, they'll be doing the buildings for their own consumption. And your community resident shelters, construction worker housing, educational, everything else will fall in this category. In this, the outlook also changes a little. They are not only looking at low capital cost, but they're also looking at low maintenance. Now, how is this going to link to the deliverables that we have set in the project? Just a minute, I'm just trying to. Yeah. So for example, the people who are bothered with build and sell may be convinced only with the construction cost optimization and the financing cost optimization. For them, life cycle cost analysis may not be something that will convince them. For rest of the folks, the build, own, operate, or build, own, live, for these folks, even if your project cost is going higher than what they have anticipated, you can rely on life cycle costing to be able to justify why you are doing what you are doing. Now let's move further. Just a minute. And this is something I want to, draw your attention to. To make it more affordable, you will be focusing on these 4 parameters, like you are trying to reduce capital cost, hard costs, you're trying to reduce soft cost, you're trying to reduce operational cost. Hence, you're trying to prove you reduce the life cycle cost, etc. But while you are also calculating how you are reducing, you should also try to see what value you are adding. The value you are adding may not be a tangible value. You may not be able to calculate it, but you'll be able to articulate it. For example, if the livability has increased in that building, of course, it'll command a higher, rental or a higher sale price. If the resilience has increased, it'll also increase the livability. And if the asset longevity increases, that will also reduce the replacement cost, maintenance costs of the owner. So in short, how you are actually increasing the value of asset, this also you guys pay attention to and make sure that you highlight it to your project partner as well as your jury members later. For this webinar, I'm just taking one example. I'm trying to take a office building where it's a build, sale or lease kind of model. So the expectations could be low capex and high sale value. So once this is the journey that you will be taking, because I have seen some of your deliverable 2 reports. I've also seen some of the information that you have filled in your project forms in terms of your project costing, project sizing and other things. So I thought I'll just tell you, if I were you, how will I approach to establish a base case? Because establishing a base case is a very important thing for you to prove that you are making an affordable building. So you will naturally collect the basic, project information, that what is the site area, what is the FSI, what is the ground coverage, what is the allowable built-up area, if he wants to build, how many number of floors, etc. Whatever expectation that the project partner has and the building bylaws allow, you'll understand. Then you'll also try to get either project budget or project cost. For example, if somebody has not detailed out, so your project partner may be having a project which is coming up 5 years down the line. He may not have worked out much. So he knows, like, okay, I'm going to make an office building, but in this vicinity, the other office buildings are going to be this much. Or he may say, like, okay, my budget is 2,500 rupees a square feet or 25,000 rupees a square meter. He may give you a target. So that's one way. And some other project partners may be in a little more, advanced stage. They may be able to tell you clearly what is the land cost that they're going to incur and how much they're going to spend on civil works, MEP. If you are already working on a project, that project partner is about to build in a year or 6 months, or the construction is about to start, usually they'll be having all this kind of information. And most of you may be collecting this information and assuming this is the total cost of the project. But this, just adding up land costs, civil works, MEP, landscape, equipment, internal fit outs, and even you add contingency also, this is not the total cost of the project. This is basically the total hard cost of the project. Because for you to be able to convince your project partner things are affordable, you will need some more information than this that you all may be gathering already. So just a minute. This annotation is a little tricky. Yeah. So what information further you'll need is, you'll need to understand the project financials, in the sense like what is the timeline for the project. So that is something that you will need to understand. What is their timeline, and what kind of are they taking loan? Are they doing it on their own? If they're taking loan from the bank, how much they are taking, what kind of interest, when are they supposed to pay it back, and other things. All these things will help you convince to do to your project partner how you are making your project affordable. Just a minute. So in short, you will be also collecting the soft costs. What are the pre-operative expenses that the client is going to incur, and how much consultants are going to take? What are the kind of interest during construction that they are going to incur? So together, once you have the total hard cost, total soft cost, only then you're able to establish the basic project cost. Now, some of you may be thinking like, in one or two reports I have seen, just a minute. In one or two reports, I have seen this aspect that people are confusing the base case with the proposed case. Base case is simply how your project partner is going to do the building on his own without any net zero energy measures, what he would have done without your intervention. So that is the parameter that you want to understand. That is the cost you want to establish. If you are not able to get these kind of information from the project partner, look at your self-learning module. They have shown what kind of resources that you can look at, CPWD schedule of rates, or any references from the state government bodies or central government bodies you can take to establish your own benchmark cost. Okay. And once you have collected all the information, you will basically be able to understand this thing. Now you have a clear grasp now. Okay, this entire thing is my hard cost. To what extent is the soft costs that are there involved in the project? Which of the aspect is consuming what? So what kind of intervention that you taking is going to make a difference? So this kind of, if you get all this information, that will help you establish your case in a better way to the project partner. So now comes, when do you start working on the affordability? Like, in the conceptual, like energy simulations, you started working at the conceptual stage only. Design, you started working at the conceptual stage. Material selection or something, you're starting at like once the concept is finalized. But when do you work on the affordability? Affordability should be taken into account right from the beginning, right from the way you are understanding your site, the way you are preparing your base model for your energy simulations, and the way you are establishing the parameters. So like the way you have established the base case for costing, you also establish your base case energy model also, which will help you analyze things further, like I show. Like now I'll take up the first aspect. How do you look into construction cost optimization strategies? So you are hearing this word right sizing. Okay. So I'll not emphasize much on the use of local or repurposed materials, but right sizing, I want to take you through certain, interpretations. Like, okay, right sizing can also happen if you understand your bylaws proper, in the sense like, if you remember correctly, your project partner in this example has asked you to do a 20-floor building, but his FSI is only 20%, government mandated. His ground coverage is, let's say, 25%. So FSI 2 and 25% coverage may be only 8-floor building. If it's 40% ground coverage, he may need to build only 5-floor building to be able to satisfy the building bylaws. But does this have an impact? Like, why do you need to look at this aspect is something that I want to show you. Impact of building bylaws. So this is your project partner requirement, a 20-floor building, and number of floors that are required based on the building bylaws is like, let's say, 5 floors. Now, if you do even a basic thumbnail model also in any energy simulation software, you can set any kind of parameters. You don't need to worry whether I'm picking the optimum parameters or suboptimum parameters. You take any ASHRAE base case model parameters, you set the occupancy schedule. Basically, you apply the same parameters. And when you see, you'll see the results. Results will sort of surprise you. All these 3 buildings have the same kind of specifications, same kind of occupancy, same kind of scheduling. So because of that, the lighting and equipment may be the same, the energy consumption between a 5-floor building and a 20-floor building. But if you see the air conditioning energy usage, it has reduced substantially. So this, you may think like, okay, this is a OPEX fala measure. But because of the heat load is reducing, your chiller plant size is also reducing. Instead of 465 tons, now you only need to buy 345 tons, which means like you have saved money, and you're also consuming lesser amount of lift energy. That's because you need lesser number of lifts in a low-rise building compared to a high-rise building. So this way, if you understand your bylaws, this is one way in which you can, sort of establish right sizing. Another way that similar kind of thing, another way that you can do is understanding the building program. If you understand the building program properly, that will also help you save some costs. Like, this is one exercise we had done. This is a 5-floor building. Like, this is just drawn for your convenience. So this is the stilt. This is a 5-floor building. There are like 4 towers, and at the roof level, so there's a roof level, there's a 5-floor building. In this building, all the cyan marked things that you are seeing are the eateries that the architects have planned. So we try to analyze whether the allocation was correct or not. So when we try to right size the architectural programming, what if we do different kind of allocation? How many people bring lunch from home? What kind of space that you need to do? What kind of shifts are there? Can we multitask the space? So if you right size the space, if you right size the circulation, and if you multitask usable spaces, you will realize that you will be able to save quite a bit of these things. Like, suppose in this iteration, we had done a lot of options we have analyzed to see like what kind of size requirement is there for the eateries. This is the number of seats, and this is the total area that's required. So for the final option, which satisfied all the functional requirements, resulted in 3.5% area reduction for the total project size. So instead of building 100, we can only build 97, 96.5. So this resulted in 3% lesser total project cost. So that means this much 3.5%, instead of allocating to eateries, now the developer has 2 options. He can choose not to build this 3.5%, or he can choose to build this 3.5% and make it a leasable space, make it part of the office space, increasing his rental revenues. So In this way, you are basically making it, making the building more efficient. You're reducing, you're right sizing through architectural programming. So keep little good eye on the architectural programming part. In the same way, structural system also, how can you leverage structural system? Can you use this to be able to right size your building? So for example, if you are taking a conventional RCC column beam structural system, so there are two things that happen. If you, a typical office building, one grid will be, let's say 10 meters. So if you want to span 10 meters between column to column, your beam depth will be almost like 1 meter or 0.6 meter based on what you're doing. So basically you have the beams, then you have to give false ceiling for the ducts, then you have the floor. So typical floor to floor height basically happens to be around 4.2 meter kind of scenario. Instead of that, if you had explored any new structural system, such as, let's say, pre-stress post-tension slabs or any other technology that you have used, now here, what happens is the beam depths may become barely 100 mm instead of 1000 mm. And you'll also be able to construct this thing much faster. It's going to take lesser time and it's going to take lesser height. So this kind of thing, will result. So both the buildings, whether you are constructing in RCC, whether you are constructing with PT slab, the usable area for the occupant is exactly the same, in the sense the internal height, the usable height that's available for the tenant or an occupant is exactly the same between both the buildings. But the total height of the building reduced by 14% in a 10-floor building or 5-floor building or anything. So this will also, if your height is reducing, that will also have a ripple effect. Instead of having this longer pipe, you'll have shorter pipes. Not only the structure is going to cost more, it's also going to result in reduction of facade costs. It's also going to result in your facade cost reduction. So if you see the RCC work, it may not have reduced much, but your painting work will reduce because the size of the building is lesser. Your glazing work will reduce. Your plastering, you're reducing. The amount of masonry that you're doing is lesser. The amount of shuttering you're doing is lesser. So all these things also will result in further savings beyond just the structural, hard cost reduction. In the same way, you can also look at your window to wall ratio optimization. The good parameters may say like you have to have 40% window to wall ratio average. So one way to do 40% window to wall ratio is like you are putting the same size of windows everywhere, or you can actually do your simulation parametrics and see, can you have larger windows somewhere, smaller windows somewhere? You can see the iterations. Now, in the last iteration, the facade cost is lesser, even though we have much larger windows. On the north side, instead of 40%, now I have 80% size windows. On the south side, instead of 40%, I have 50% size windows. East and west, I have reduced. On the whole, I am also reducing air conditioning loads. I am also reducing the chiller size. I'm also reducing the facade cost while optimizing and increasing the daylight penetration. In the same fashion, like what do you say, this is one aspect about the materials, local materials. So one of the things that you'll hear is like if you want to do a low energy building, low efficient building, the bylaws and or the guides may say like you have to have a glass or with shading a solar heat gain coefficient of 0.2 or 0.25. So 0.2 to 0.25 glasses tend to be soft coated glasses, which are imported, which are expensive. Suppose this here is the energy consumption from your regular double glazing, clear double glazing. This is the energy consumption from a SHGC 0.2 class. Both are unshaded scenario. Even when you get into the shaded scenario, once you do optimal shading, you see how much optimization that you are able to do in the top line, in the clear double glazing. And in the same way, if you have done light shelves and proper shading, your clear double glazing is almost as, your clear double glazing, your clear double glazing now with the light shelf and shading, everything locally manufactured, is almost as efficient as the imported SHGC 0.2 double glazing unit. And if you see the difference between a highly efficient glass being shaded versus your clear double glazing glass being shaded, the difference is much lesser, but the cost advantage will be much higher if you are trying to use local materials, if you are trying to optimize. This is not a hypothetical scenario that I am saying. Suzlon One Earth building, which has got LEED platinum rating, TERI 5-star rating, has got almost 75% of the glazing is clear DGU, which is protected by top to bottom louvers, like you see in this picture in the middle floors. So this is something that's possible. And another area that you should focus a lot to be able to right size. Right size is focus on cooling. I think you must have seen the webinar by Peter Ramsey where he has explained you the similar kind of scenarios. So without actually getting into the advanced simulation or picking anything, if you do the right massing layout orientation, and if you reduce actively cooled areas, if you are relying cooling with passive means, and if you are trying to shave the peak loads or shift the peak loads, you will be able to achieve a lot of substantial saving, which you can demonstrate through your costing. For example, in this Suzlon One Earth building, the original load without any of the measures was like 1905 tons. And we used louvers, we used double glazing, we used insulation, we used LED lights, we used heat recovery, everything possible that we had done. Still, we could not go beyond 37% optimization. The one way that we could actually get into the LEED Platinum or TERI 5-star, anyway, that time the client wanted to get these kind of ratings, to be able to reduce our cooling load or the chiller sizing. One thing that we have seen is like we multitask the areas, the common areas, and we try to cool the common areas through heat recovery and indirect evaporative cooling, where we decided not to use any kind of active means throughout the year for the cooling of these areas. These areas, thermal set point was also, instead of 24, we set it to 27. So through this, we were able to actually reduce our chiller plant size from 1900 tons to 997 tons. And we also reduced the energy consumption by 48%. Another area that you should potentially look at is your free cooling potential. This will be very good if you are able to design your HVAC to be able to use free cooling, like how you are designing your AHUs, how you are doing the duct sizing. If you're already doing a radiant building, you will be at an advantage because you will be using dedicated outdoor air system, like Peter must have explained already. And this is the right side chart is basically the green areas, green shaded bars are where we'll be able to use free cooling via water side economizer in a span of a year. So during these times, during these months, during these many hours, we will be able to run the building without actually using a chiller. So this could potentially reduce your annual energy by 10%. You can also reduce your cooling energy by 30% in a climate like Gurgaon. And if you're in a benign climate, you'll be able to see far more benefits. So like reducing the hard cost, like for example, in the HVAC thing, Peter also must have shown you the things. I'm just trying to highlight how low energy cooling, like radiant slabs, can actually cost lesser than more. Like suppose in the building example that I've showed you for the 10,000 square meter, if we were going the conventional route, we would have required 350 tons of chiller, which would have costed, let's say, 53 rupees per square foot of built up area. If you are doing radiant cooling, since you have already used all the other measures, shading, good lighting, form, mass, everything, you have reduced your heat load substantially, and your chiller plant sizing also has come down to 150. Even though you're buying an expensive chiller, and even though you are investing into the radiant slab also, your cost per square foot for the cooling for the chiller plant is going to come down. Another thing is like conventional building to radiant buildings, the number of AHUs and the ducting also is much lesser. Instead of 20,000 CFM AHUs, 9 numbers, you can do the same thing with 8,000 CFM DOAS, 2 numbers. So instead of spending 62 rupees a square foot, you can do the same thing in a better way in 12 rupees a square foot. Your chilled water piping may be the same, it may not differ. Your ventilation fans may be the same. Even though if you have added 55 rupees more for the radiant slab and all the other systems also, your total cost, as you have seen, is lesser than a conventional system. That is because of you right sizing. In right sizing, you're not only replacing a low efficient system with a high efficient system, but you're also reducing the size of the high efficient system. Okay. So basically, this is what happens. A well-designed radiant system has 5.9% lower capex than any conventional HVAC system. This is true whether it's a residential building or whether it's an office building. In both scenarios, radiant works quite well. And your chiller plant size can reduce even up to 57%. And your AHUs will drastically reduce. And number of AHUs reducing also will result in a good side effect. In the sense, like if you are building lesser number of AHUs, you are also freeing up that space as a leasable area. In this building, instead of doing conventional, since we went to radiant, we almost freed up 1.42% of building area from converted it from AHU spaces to leasable office spaces. So that kind of advantage also will be there. So you keep your, eyes open to all the possibilities. Now, when it comes to financing costs, how do you, reduce the financing costs? What are the financing costs? As you have seen in the beginning that we have identified in the project cost structure, the IDC, interest during construction, is amounting to almost 8% of the total project cost. So, and reducing this is reducing the soft cost. IDC is a soft cost. Okay. And so one way is like, suppose if you are doing a building which is going to take 3 years in the conventional manner with RCC, you can do the same building in 10 months if you are doing it in composite steel and metal decks. So this can reduce your construction time by 45%, which means that's the amount of time that I don't need to pay interest during construction on. And it'll also mean that my operations, my revenues will start 1 year sooner than anticipated. So like you have seen, like this will, like in this case, in a conventional RCC structure with VAV versus steel plus radiant, one aspect we have reduced is, let's say, the MEP works. MEP works have come down by 8.7%. even though the civil construction cost has gone up, because steel structure is going to obviously cost substantially more than the concrete structure. Your landscape may be the same, your equipment and everything may be the same. Your contingency will come down because your total capex has come down marginally. Your total hard cost has come down only 0.1%. But if you see the major, you may say like, okay, it has not made much of a difference in the hard cost. But if you see the soft costs, the interest during construction has come down by 44%, which results in the total project cost reduction. And this also results in you taking smaller amount of loan than you were taking before. So almost 7.3% of the cost saving can be seen just because of the interest during construction, which is a direct translation of the smaller amount of time that you have taken using a steel building. And now the third aspect, life cycle costing. Life cycle costing, you need to get into if you are not able to illustrate your point. Like in this case, in this scenario, if you are able to do your net zero energy or building and illustrate through soft cost reduction, hard cost reduction, that your total project cost is lesser. If you are in this scenario, you don't need to even get into the life cycle costing. Suppose if you are in a scenario where your total project cost has gone higher than your baseline cost, that's when you have to basically look into your life cycle costing, the total cost of ownership. So in this, you are not only looking at the capital cost, which is also a compilation of the soft costs and hard costs. You're also looking at the operational expense. Every year, how much operational expense it's taking in terms of electrical bills, water bills, your maintenance costs and everything, and what kind of replacement of parts or equipment that's needed, and what kind of disposal that you need to do with all the wastage that comes out, and what is the residual value of the asset that's left. So you are basically looking at the full life cycle cost of a life cycle cost of the building to be able to justify. For example, and in life cycle costing also, I'll just give you some insight into the financial metrics. Some people may be using payback period. That is one metric everybody uses, quite popular. Like suppose if they say like, okay, this building is going to cost more, you may say like, okay, this is going to cost X amount of money, and the savings is going to offset the higher cost, and you will be able to recover all your all the over extra money you have spent in a period of 2 years. So that kind of thing is one way to justify. But when you face different scenarios, payback period may also mislead you. Like for example, in these three scenarios, scenario 2, scenario 3, scenario 4, where the capex infusion is different from each other, and your annual savings in the opex are also differ, your payback period may be showing exactly the same thing. Okay. And similar kind of thing, internal rate of return, IRR, is another metric everybody use in how much time your whatever investment that you have done is coming back. So this also works in some ways, like the higher IRR is a better project, but that also IRR also fails phenomenally at some places. Basically, what you have to look at is net present value. Net present value is the basis with which life cycle costing also operates. When you look at the net present value, you're basically taking all the cash flows or the potential savings that you are going to incur during the lifespan of the building, and you are discounting it at the hurdle rate or interest rate that you want to take, and you're seeing what is the net present value of all the cash flows. So in that scenario, whatever building that has got the highest NPV, or in case of expenditure or something, you look at the lowest. In case of return, you will see the highest return. Okay. So these kind of things also will help you. And I'll just show you one life cycle costing example, and then we can conclude. Just a minute, there's something happening. So for example, we wanted to reduce. So in this case, let's say there's a scenario, the conventional HVAC system is costing 161 lakh rupees. And we decided that radiant cooling system is going to cost us much lesser. But because of our operational problems, let's say we are not getting electricity during the peak hours. If you see this line, this is like 0 hours to 24 hours. This is the, let's say, the operational cycle of the building during the daytime, 10 to, let's say, 7. So this profile is your cooling demand load profile. So let's say the building is starting at this, the amount of cooling energy that's required, or the amount of tonnage of chiller that you require to cool while the building peaks, is what decides the chiller plant sizing. Okay, let's say this is how they'll size. Like if I look at the cooling profile, which you usually get it from your energy simulation model, let's say I need a 2000 ton chiller, but I wanted to reduce my, what do you say, capex and everything. I want to optimize the whole scenario. And I may say like, okay, I will not operate the chiller during the day between, let's say, 12 to, let's say, 6 o'clock, when the peak load or the power demand is so high that the government is not able to supply during the summertime. Your what do you say, power supply is not there. People are relying on generators. The generator is going to cost, let's say, 3 times more than what you are doing with the, what do you say, conventional power. You are not able to do anything. So in these kind of scenarios, somebody will come and say like, okay, why don't we make a thermal energy storage tank? We'll run the chillers during the night only, and we will charge the what do you say, tank with the coolness, and during the daytime we will discharge all the coolness we have stored into the tank to run the building. That way, instead of buying a 2000 ton chiller, we'll only be able to manage with a 900 ton chiller. So here you may think like, okay, you have reduced the size of the chiller, so it's costing more, but you're also building a huge what do you say, water storage tank, and you're insulating it, and you are incurring additional piping, additional maintenance, additional kind of all the other things. So which all of these things may drive up your capex in this scenario, like 179 lakhs instead of 161 lakhs. But in this case, if I look at the life cycle costing, I'll be spending much lesser on the energy, even compared to radiant cooling, because during the day I'm not even using the chiller when the peak electricity charges are there. During the night, when the charges are low, that's when I'm using the chillers to the maximum. So in this scenario, if you do the life cycle costing, you will be surprised. The life cycle costing is much lesser than even the radiant cooling or even the conventional building. So if somebody is going to build the building, own, operate, or own and live, they will now see, okay, even though you're spending more capex than what I want, I see the merit in spending this thing because it's leading into substantial savings, and it's also future proofing my building quite a bit. So this is how you can basically look at the life cycle costing. Yashma, are we running over the time, or can I take 2 more minutes?
Yeah, 2 more minutes is fine.
Yeah, 2 more minutes.
Yeah.
So I just wanted to, what do you say, give you a basic example of IRAD. IRAD is one building done by architect Ashok Lal. It's one of the good examples for you to look up when you're looking for any sustainable or low energy building. So phase 1 of the building, they have used all the good principles of shading, massing, insulation, and everything. They have also done a good VAV building, VAV, what do you say, air conditioning system, which is highly optimized to the best amount possible. This is phase one that's constructed. When they were constructing phase two, that's when Ashok Lal and team sort of try to explore, try to bring in little better consultants or new experts, and they try to explore what if we go to radiant system. So they have designed this whole building for radiant, and they have said like, okay, this requires 49 tons of cooling. And when it comes to ordering the chillers, they have realized collectively, and the same consultant who has done the energy models and everything also done the energy modeling for the phase one, and also looked at the existing energy bills and saw that the actual peak load of this building is 91 tons, the phase one building. But the installed chiller was 150 tons in the phase one. They have actually bought a 150 ton chiller, and they were using the 150 ton chiller to run phase one alone. So when it came to phase two, then they saw like, okay, one is like the peak load. These two are the peak loads, 91 plus 49. But what is the average operational load most of the year? Like 80% of the times, you're not peaking. That turned out to be 85 tons for both the buildings. So now what these people have done is, instead of buying a new 49 ton chiller, they bought 185 ton chiller. With that, they were running both the buildings 80% of the time. They used the existing 150 ton chiller as a backup chiller, only for 20% scenario when there was a requirement. A, they created redundancy. They have a safe backup. B, instead of running 150 ton chiller plus 49 ton chiller, they are basically making do with a 85 ton chiller, which was circulating things to both. And they have also done it in a very smart manner. The 85 ton chiller used to supply water, chilled water at 7 degrees to the phase one building. Whatever chilled water that was coming out from the AHU was coming at 12 degrees. That 12 degrees centigrade water, they used to put it into the radiant slab of phase two, which used to come out at, let's say, 16 degrees. Now this 16 degrees, they used to send it back to the chiller and cool it to 7 degrees. So that way they were able to multitask and come up with a system which was quite interesting. And so this is sort of a smart sizing strategy. So Yashima, I'm done. We can take questions if there are any.
Yep. Thank you, Jagdish. Yes, we have a few questions.
Should I stop sharing my screen?
Sure, yeah. Yeah, I have done that. All right, our first question is, so XPS requires a lot of joints and it needs a lot of workmanship. Puff, on the other hand, offers easy compared to XPS, but same time it's also costly. Any incremental study that you have done? I think, Mansi, this is a question for you.
So this is an interesting question. We have done studies on this. However, for the participant, what I would suggest is you could reach out to your project partners particularly, or you could reach out, do a little bit of market survey, check the installation companies which are offering, probably Dow or Pidilite does this kind of work. So probably you could reach out to them and get the cost data out for both of the same. But yes, I pointed out correctly, there would be a difference in terms of applicability of both of the same.
Right, thanks, Mansi. Next question, which are the softwares typically used for architectural programming or optimization packages used in the industry? Jagdish?
Asad, unfortunately, there's no specialized architectural programming software. I can only think of two things. What we do is like, it's manual and Excel, usually. And like Mansi pointed out, now with the energy simulation tools and also the BAM tools, the way you are able to take out areas is becoming much more easier. If you're doing your conceptual modeling, ideal world scenario, if you had done your conceptual modeling in a BAM software, which could potentially export it to a, your simulation software, That way you have best of the both worlds. Whatever you have changed, architectural programming here, not only you'll get a spreadsheet, but also you'll be able to get the energy modeling numbers. But at the end of the day, you have to manually compile things in Excel and use your judgment. There's no special software as such right now. Mansi, you want to add to that?
No, I think I agree with you on that, Jagdish, that definitely we can do that exporting, but end of the day, we have to do it and figure it out on our Excel or the data
And
written basis.
Architectural programming requires a much more experienced professional compared to anybody who does building design or HVAC design or even energy simulations. This is somebody who can think through business cases, use cases, how the things are working, how the lifestyles are evolving. So there's no linear, straightforward way in which you can be taught actual right sizing of architectural programming.
Right. Thanks,
Want to add
Jagdish.
anything? I think Prasad is best fit to
Yes,
to this thing.
I was going to move on to him. Prasad, would you like to add something?
Am I audible?
Yes.
Yes.
Yeah. No, actually, I don't have anything to add, even though I'm audible.
Only we're just dragging you, that's all.
All right. So we do not have any more questions for today. I'll wait for a minute or so if anyone wants to ask anything to our experts. If not, we will close for today.
I wanted to say something else, though.
Yes, please, Prasad.
Yeah. So I think that, I think we've got some 28 attendees over here in today's webinar. And, the affordability contest for Solar Decathlon India is quite important because you can come up with all sorts of fantastic solutions for your, Solar Decathlon India, net zero energy, water resilient buildings, etc., with fantastic innovations. But unless you really understood the costing aspect and understand how to justify the costs to a potential project partner, as well as the jury, it will seem very hypothetical in terms of the way you approach your solution and the way you are trying to demonstrate what you've done. So taking this aspect seriously with maybe 1 or 2 team members continuously focusing on cost from now until the end of the competition is really, really critical. And I think, Yashima, you and Mansi, you both have been parts of, Solar Decathlon India teams. Maybe you can also speak to, how having this going on side by side with the performance modeling and all that is important. It's not just about right sizing and those kinds of things with Mansi also talked about. Those are valuable, but just having a continuous reality check on what you're doing, that with the numbers and costs is quite important.
Just one thing I want to add, Prasad. If any of the team or colleges or teams want to interact with me on your proposals to understand the affordability aspect in your scenario, please feel free to reach out either through TRG group or through Yashima, or I can share my email ID that can be circulated. If somebody wants to ask any questions or something, that I can take out sometime on every weekend and answer.
Right. That would be wonderful, Jagdish. So if anyone wants to get in touch with Jagdish, they can write at uday@solardecathlon.india.in, and then we can put them in touch with him after that. Mansi, would you like to add anything?
I think this is it from my side, Yashima.
All right. Okay. Thanks. So once again, I would like to thank you both, Mansi and Jagdish, for very informative sessions. And I hope our participants can make the best use of the knowledge that you have shared today. And thank you everyone for participating today. And we will see you soon for another webinar related to Solar Decathlon India. Thank you.